now that we developed our features, the next step is to actually transfer the features that we developed from a photoresist onto the oxide, the red oxide that we grew. For this, we use buffered oxide etch, but prior to etching the 500 nanometers, around the 500 nanometers thick film on our silicon, we need to do a calibration run. Because we are doing a long etch, it is important to see what is the actual etch rate of the buffered oxide etch we are using to avoid any over etching of our features, and as a result lose the finely structured features due to this over etch. For this, we'll use a part of a diced wafer from our run, that is a front wafer, which is around 550 nanometers. You can see that we are using half a wafer, so we can use this to use the rest of the wafer for later calibrations. But it's a good idea to calibrate our wafers, the etch rate, before we carry on with the long etch. So let's go on and etch this 550 nanometer wafer, black wafer. As you can see, the wafer that we diced to calibrate the etch rate before carrying on with our buffered oxide etch, we see that after a 130 seconds or 2 minutes 10 seconds etch, there's a thickness of around 255 nanometers. So the starting thickness, average thickness is around 515 nanometers, and the average thickness after etch is around 255 nanometers. So you can calculate the etch rate as thickness before etch minus thickness after etch by the time, that is 130 seconds. So that's 260 by 130, or 2 nanometers per second, or 120 nanometers per minute. So this is slightly higher than the 90 nanometers per minute that we were using before. So it is very important that we calibrated the etch time, or else we can end up over etching our features and losing parts of our features due to this over etch. Okay, now that we have calibrated our etch rate, which is around 120 nanometers per minute, we can go ahead and etch our actual wafer that's been patterned, which is around 4 minutes 10 seconds. We'll etch it for an extra 5 seconds to make sure that the oxide is removed everywhere. Make sure not to etch too much above the actual etch time, because wet etch is an isotropic etch, and this can create huge undercuts if you're not careful. 4 minutes 15 seconds, we can go ahead and take the wafer out. You need to rinse it thoroughly with DI water prior to inspecting the features. It's also important to check if the features have actually been etched. If it isn't etched all the way to the silicon, we need to carry on the etch for more time. Okay, now that we've etched the diffusion mask, diffusion window mask, that is mask 1, the next step is to actually perform diffusion of phosphorus dopants for the source and drain regions of the MOSFET. Traditionally, this is done using ion implant in the industry, where high energy ions such as arsenic or phosphorus are implanted onto the silicon wafer and then driven in for a certain doping profile using anneal in a high temperature furnace, also known as diffusion. But in this step, we'll be doing a similar thing, but using spin-on dopant such as P506, which is essentially a solvent with SiO2 and phosphorus ions of a really high concentration. When we actually spin it on our wafer and perform diffusion on the wafer, the phosphorus ions in the spin-on glass actually diffuse through the open areas where we etch the diffusion windows and dope those regions. The remaining regions are protected by the pad oxide, which is the other purpose of the pad oxide surface. So let's go ahead and spin on the phosphorus spin-on diffusion. can go ahead and quickly bake it on a 200C hot plate for 10 minutes. For diffusion, we'll be using cube A, which is at 1100 degrees centigrade, as you can see. We'll also be flowing a mixture of two gases, that is low flow oxygen and nitrogen. Low flow oxygen is at around a setting of 70, and high flow oxygen is around a setting of 19.5. So high flow nitrogen. So you can see that this process actually drives in the dopants, the phosphorus dopants which is not plant. As a consequence of flowing some oxygen, you will also grow some oxide, but you can remove this oxide later on in the next step and measure the resistivity of the diffusion that we have created. Now that we have finished baking our spin-on photoresist, we can go ahead and do the diffusion. This is done using cube A with a mixture of 2 liters per minute nitrogen and 3/4 liters per minute of low flow oxygen. Check it out. We need to make sure that we push it 3/4 of the way in to start with the diffusion process, and we continue the diffusion process for 30 minutes. We can pull out the wafers after the diffusion step. Make sure to pull them out carefully so that you don't end up breaking them. Now that we have finished the diffusion step, you can actually measure the oxide thickness that's been grown during the diffusion process. This is a result of the P glass that we spun in addition to the oxygen that was flown in the furnace during the diffusion step. We can measure this oxide thickness right at the edge of the silicon wafer, where the wafer was not patterned and exposed to the etch solution prior to this spin-on and diffusion step. So let's go ahead and measure the edge of the wafer. As you can see, the thickness of the P glass plus the oxide that been grown during the diffusion step is around 200 nanometers. So we need to take this thickness into account for the next etch step when we are going to etch the gate window mask. Okay, now that we have finished etching our diffusion window for our source and drain, N-type source and drain, and actually diffusing a phosphorus dopant through the source and drain regions. In the next lecture, we'll go ahead and fabricate the gate oxide, followed by mask steps for the contacts, and actually aluminum metallization to finish our MOSFET structure. Thank you, and see you next time.